for 48A. I'm going to do 48A, and I want you to do 48B exactly the same way I do 48A. So first of all, let's talk about what we have here. They gave us an equation. We're going to have to balance it and find the E cell for this, which is the first part. And then after that, so the first part, the standard EMF is E cell. Don't let that confuse you. Those two mean the same thing, E cell. Calculate the delta G at 298 and calculate the equilibrium constant K for each reaction. So there's three things that we're doing. We're going to, well, there's a whole bunch of things. We're balancing and calculating the E cell, so that's the first two. Then calculate delta G, that's the third one. And equilibrium constant is the fourth one. Okay, so now I'll walk you through it here and try not to take up too much time. The first one's actually, in my opinion here, not too bad because we've been practicing this. I think it's the most confusing, but we've been practicing this, so I think we should be getting to be pretty good at this. So here I have iodide ion is oxidized to I2. Now I think that if it says oxidized, I'm guessing it's going to be, that's going to be the iodide ion means there's two of them, and that's going to be one of the half reactions, and there's a good chance that this is going to be, that's a solid there. This one right here, and this is going to be an oxidation because, and here's why I say so, I have a total of -2 on the left-hand side, so I need a total of -2 on the right-hand side to get them to balance. So -2 and -2 on there, so that's good. So I don't have to do anything else because there's no oxygen or anything else. So all I have to do for this oxidation half reaction, this is where this happens at the anode, and that makes a difference. That's important. Is just write that. I don't have to worry about oxygen, balancing oxygen and hydrogen and water and any of that stuff. So let's go right to the reduction then. The reduction then says is oxidized to by Hg. So that means Hg2 with a +2. So I'm looking for that. That's probably going to go to, now here's what I do. I look over here and I notice that if I'm confused as to where Hg goes to, I look at Appendix E, and this is the half reaction, the only one that has an Hg2 with a +2. All the rest of them, oh no, this one does too. Okay, which one is going to be the oxidation? I'm going to assume that because you see there is an Hg +2 right there, but that one would be an oxidation, and my top one is going to be Hg2 with a +2. This is my reduction, so I'm going to have to use the top one that I highlighted. Okay, so now here's what this looks like then. So that's going to be a +2E like this, and then over here we're just going to 2 mercuries at 0 that are liquid like that. Okay, so now all I have to do, I don't have to balance anything else. I have the 2 electrons. This is so easy. 2 electrons, like this. So that means when I put them together and I write out the whole thing, I got 2 iodines with a -1 plus Hg2 with the +2. On this side, I have I2 as a solid plus 2 mercuries as liquid like that, which means E cell equals, and then the red is the one that's in, happens at the cathode, which comes first, which is 0.798. I'm going to subtract that from the iodine that I have right here, which is a minus a point, this is a positive, 536, like that. I subtract the 2, and whatever I get when I subtract the 2 is the E cell for this reaction, and it should be standard because all of them on. So let's just see what we get when I subtract the 2. I get 0.789 minus 0.536 equals 0.253 as my value. That's a positive 0.253, which means this is spontaneous. Okay. that's the first part. I did the balancing and I did the calculating with the standard E cell. So let's go right into the next part. The next part then is going to be the delta G, finding the delta G standard. Equals a negative NF for the Faraday's constant and E cell, like that. Okay, this was, what was it, 20.4, 20.5, 20.5 I think it was. 20.5 section. Sorry, I need some coffee. So notice the number, this N right here is the number of moles of electrons. So that's moles of electrons, and that would be 2. So it's a negative times 2. Faraday's constant is, what is that, 96,500 coulombs per volts or some poop like that. I forget exactly what it is. That's kilojoules per volts, moles electrons. Okay, I was way off there. So that is, so this is 2 moles, right? This is kilojoules per volts times moles of electrons, like that. And then E cell, of course, is what we just found, which would be a positive 0.253 volts, which is where volts cancels with volts. Moles of electrons cancels with moles of electrons, and what we're left then will be just the kilojoules. So the kilojoules for this then should equal a negative, holy cow, I made a major mistake here. If we change this, the Faraday's constant is in joules per volts moles of electrons, and when I change this to kilojoules here, I need to move that number of places like that. So it's actually 96.5 kilojoules per volts moles of electrons. Okay, that's very important. So Faraday's constant in kilojoules, which is what delta G should be in, you have to change the number from 96,500 joules to 96.5 kilojoules. And then what I get then is a negative 48.829. Once I multiply all of these in, I get a negative 48.829 kilojoules, which you could probably shorten off to 48.8. But we're not finished yet. I'm just about done. Hang with me here. I'm going to go a little bit further down. That means now I'm looking for the equation for the equilibrium constant. So I'm going to do that one in the next video because I need to set this up. Okay, so the second part of number 48.